Alright guys, in this video I'm going to be going through everything that you need to memorize for A-level Inorganic Chemistry. Now before we get started, make sure you like, comment and subscribe, and make sure you check out some of my other videos. So we're going to begin with period 3, and firstly we're going to start off with the reactions with water. So when sodium reacts with water we get when magnesium reacts with water we get and when magnesium reacts with steam we get. Okay, so you also need to know the reactions between the period 3 elements and oxygen. So when sodium reacts with oxygen we get, and we see a white flame for this, and the sodium oxide is a white solid. Then for magnesium we get the reaction for aluminium is and then for silicon we get then for phosphorus we have then for sulfur we get to prevent them from reacting with air, sodium is kept under oil and phosphorus is kept under water. The metal oxides are ionic, therefore they have high melting points due to strong electrostatic attraction between oppositely charged ions. SiO2 is macromolecular, so lots of energy is needed to break the strong covalent bonds. So it has a high melting point. The simple molecular oxides have a low melting point, as you only need to break weak van der Waals or permanent dipole forces. Metal oxides react with water to form an alkaline solution. So for example, when sodium oxide reacts with water we get 2Na plus and 2OH minus. And with magnesium oxide we form Mg2 plus and 2OH minus. Since aluminium oxide is a very strong ionic lattice and silicon dioxide is macromolecular, they both do not dissolve in water. Simple molecular oxides react with water to form acids. So for example, phosphorus oxide reacts with water to form phosphoric acid. Then sulfur dioxide reacts with water to form sulfurous acid. Sulfur trioxide reacts with water to form sulfuric acid. Aluminium oxide is amphoteric, meaning it can react as both an acid or a base. So when it's reacting with hydrochloric acid, it's going to act as a base, and the reaction looks like this. And when it reacts with sodium hydroxide, it's going to act as an acid, and the reaction looks like this. Metal oxides are basic, so sodium oxide reacts with hydrochloric acid to form, and magnesium oxide reacts with hydrochloric acid to get. Simple molecular oxides are acidic, so phosphorus oxide reacting with sodium oxide forms sulfur dioxide reacting with sodium hydroxide produces sulfur trioxide reacting with sodium hydroxide produces Silicon dioxide has a giant covalent structure. Its strong covalent bonds prevent it from dissolving in water or weak solutions of alkali. However, it would react with concentrated sodium hydroxide, and the reaction for that is because it can react with sodium hydroxide, it's classed as an acidic oxide. Okay, so now we're on to transition metals. A transition metal is an element with an incomplete d sublevel in atoms or ions. A complex is a central metal ion surrounded by ligands. A ligand is an atom, ion, or molecule which can donate a lone pair. The coordination number is the number of coordinate bonds formed to a central metal ion. Dentate ligands form one coordinate bond per ligand. Bidentate ligands form two coordinate bonds per ligand. So for 1,2-diaminoethane, the lone pairs are on the nitrogens. Then for ethane dioate, the lone pairs are on the negative oxygens. Multidentate ligands form multiple coordinate bonds per ligand. So in substitution reactions, the ligand that we're adding replaces the ligand already connected to the central metal ion. So in this case, we're going to replace all of the water molecules with 6 molecules of ammonia, and that gets us each ammonia molecule replaces one water molecule because water and ammonia are similar in size. Now in most cases, 6 molecules of ammonia is going to replace 6 molecules of water, and the opposite is true. However, you do need to know this certain example, which is when we have hexa aqua copper 2+ ion, we can add 4 moles of ammonia, and we get this. And this complex that we formed is a deep blue solution. We could also add chloride ions, and the reaction for this looks like. And this complex that we formed is a yellow solution. Notice how it only takes 4 chloride ions to replace 6 water molecules, and this is because chloride ions are bigger than water molecules in terms of size. One thing to take note of is that when solid copper chloride dissolves in water, we get when we're adding bidentate ligands, remember bidentate ligands form 2 bonds per molecule. So one of these molecules can replace 2 of these molecules. So the reaction looks like this. Okay, and with EDTA, well, EDTA is a multidentate ligand and it forms 6 coordinate bonds. So we get, and notice here how the overall charge is -2. That's because the copper ion is a 2+, and the EDTA is 4-. So when we add them together, we get -2. And we're also left with 6 water molecules. The chelate effect is when there's a positive entropy change. When bidentate or multidentate ligands substitute monodentate ligands. So there are more molecules in the product than the reactants. Now when the coordination number is 6, it's probably going to be an octahedral. When you have 2 coordinate bonds, it's probably going to be linear. When you have 4, it could either be tetrahedral or square planar. Now usually it would be tetrahedral. However, if the metal ion is one of these 3, then it's most likely going to be square planar. Now for this molecule here, we can see that the atoms are opposite each other, so it's going to be trans platin. Whereas on this molecule here, the atoms are on the same side, so it's going to be cisplatin. So in this case, the chlorines are 180 degrees away from each other, so that's going to be trans. And here, the chlorines are not 180 degrees away from each other, so it's going to be cis. Okay, and remember, optical isomerism is when the two molecules are mirror images of each other. Now, some of the reasons we get color changes in transition metals are the type of ligand, the oxidation state, and the coordination number. Transition metals show color because d orbitals split into different energy levels. Electrons are excited from a lower to higher d orbital, absorbing visible light. The color observed is the complementary color of the light absorbed. Now the two formulas for this are the difference in the two energy levels is equal to HV, which is equal to Hc over lambda. Changing a ligand or the coordination number changes the difference in energy levels, which means that the frequency of light absorbed changes. If there are no d electrons or no space in the d orbitals for electrons to transfer, then visible light can't be absorbed. Now to measure the concentration of a solution, we can use spectrophotometry. So what we can do is we shine white light through the sample and it hits a detector. And this detector measures the absorbance of light. So the steps are: we add an appropriate ligand to intensify the color. Then we make up solutions of known concentrations. We measure the absorption and plot graphs of the absorption versus the concentration. So when we do this, we plot a line like this. Then we measure the absorption of the unknown solution. So let's say we get somewhere here. We can go on this line and then go down to check what the concentration of that solution is. Okay, so you need to know the oxidation states of vanadium in all of these, which is, and the colors are, and zinc is used to reduce the vanadium from the +5 here all the way down to the +2. Okay, there's some common titration reactions that you should know of by heart. So this first one looks like this. And the MnO4- is purple. And the Mn2+ is colorless. Then the second reaction looks like this. And the third reaction is Heme is an iron 2 complex with a multidentate ligand. Oxygen forms a strong coordinate bond to iron in hemoglobin. However, carbon monoxide can form a stronger coordinate bond to iron, preventing the transport of oxygen around the body. A heterogeneous catalyst is in a different phase from the reactants. It's usually a solid. The reactions take place at the active sites on the surface of the catalyst. If we increase the surface area of the catalyst, we're maximizing how efficient it is. Sometimes a support medium is used to maximize the surface area. Now how these types of catalysts work are these three steps. So first we have adsorption, which is when the reactant molecules form weak bonds with the surface, and then the reaction happens. So the bonds in the reactants are broken and new bonds are formed. Then we have desorption, and this is where the products leave the surface, freeing up active sites. So a specific example you should know is the contact process. So this is the overall reaction for the contact process. And the second step looks like this. Another process you need to know is the Haber process, and the reaction for that is catalysts can become poisoned by impurities, and as a result become less efficient. A homogeneous catalyst is in the same phase as the reactants. The reaction proceeds through an intermediate species. So an example of this that you should know is this reaction here. Basically, this reaction is slow, and that's because there's a repulsion between these two negative ions. So what we can do is add Fe2 plus to the reaction, and we get this. Okay, and for the ion to act as a catalyst, its electrode potential has to be in between the other two ions. Okay, so autocatalysis is when one of the products catalyze the reaction. So an example of this is this reaction here, which is... Now if we don't add another catalyst, the Mn2 plus here is going to act as an autocatalyst. So the reactions for that is okay, so Ag plus usually forms linear complexes. And another thing, so silver chloride dissolves in dilute ammonia. Silver bromide dissolves in concentrated ammonia. And silver iodide doesn't dissolve. Okay, so now we're finally on to the last chapter. A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. Now when you have a hexa aqua complex, if it's a 3+, that's going to be more acidic than a 2+. And that's because the 3+ metal ion has a higher charge density, so it has greater polarizing power, which attracts the water molecule more strongly. This weakens the OH bond, making it easier to break and release H+ ions. So in here, for example, the hexa aqua complex is going to act as an acid. So one of the water molecules here is going to donate a proton, and we get... And then the complex that we formed can react as an acid again. And then this complex can go ahead and donate a H+. Now when memorizing colors for this chapter, all you really need to remember are these few colors. So when something's a solution and when something's a precipitate. So when Fe2+ is a solution, you get a green solution. And when it's a precipitate, you get a green precipitate. When copper 2+ is a solution, you get a blue solution. And when it's in a precipitate, you get a blue precipitate. When Fe3+ is in a solution, you get a brown solution. And when it's a precipitate, you also get a brown precipitate. When aluminium is a solution, you get a colorless solution. And when it's a precipitate, you get a white precipitate. This complex here is a deep blue solution. So to actually form the precipitates that we've talked about here, we need to add enough hydroxide or ammonia to form a neutral complex. So here we've got some examples. So the amount of hydroxide ions or ammonia that we add is the same as this charge here. So we're going to add 2 hydroxide ions, and then the complex is going to act as an acid and donate 2 protons from the water. So So what happened here is that two different water molecules each donated a proton, and that proton reacted with the OH minus. So if we do that same example for the rest of the reactions, we get okay, and to predict the colors that we'd see, we use a table that we drew up before. So for example, here we have a copper precipitate, and that's going to be a blue precipitate. The aluminium one is going to be white. The iron one that was formed from a Fe2+, so this one here is going to be a green precipitate. And this one here that was formed from a 3+ is going to be a brown precipitate. This complex here is amphoteric, so it can react as either an acid or a base. So when it reacts with hydroxide ions, it's going to act as an acid, and we get, and you want to make sure that you have excess hydroxide ions. And when it reacts with H+, it's going to act as a base, so we get. Now in this reaction here, we get a ligand substitution, and it looks like this. Now when we react 2+ complexes with carbonates, we form metal carbonates. So with hexa aqua ion 2+, we'd form this. And this is the case with all 2+ complexes. And the ionic equation for this would look like this. And this is a precipitation reaction. And with 3+ ions, we would form this complex. And carbon dioxide. So for hexa aqua ion 3+, we would get this reaction. And this is an acid-base reaction. Now here we have a solid formed, and we also have a solid formed over here. And the colors of these solids, well, we can work that out by using the table that we drew up earlier. So wherever the colors that we get here are what colors these are going to be over here. So for example, for the iron carbonate, well, it comes from a Fe2+, and from here we can see that the Fe2+ forms a green precipitate. And here, well, this complex here comes from an Fe3+, and from the table we can see that Fe3+ forms a brown precipitate. Okay, so that's it for A-level inorganic chemistry. If you enjoyed the video, make sure you like, comment and subscribe, and make sure you check out some of my other videos.